Hello, this is Professor Kuehn. Let's continue our discussion of Ptolemy's Almagest. This is from A Student's Guide to the Great Physics Text, Volume 1, Chapter 5. I would like to talk specifically about page 47, Ptolemy's Chapter 5, that the Earth is in the middle of the heaven. In this chapter, what Ptolemy is going to argue is that if you consider the celestial sphere, that enormous sphere of fixed stars, the Earth is located at the exact center of that celestial sphere. And in this chapter, he provides arguments, that is, reasons why he thinks that that is the correct location for the Earth. So in order to do this, I'm going to make use of some diagrams that I've prepared. So the first thing I'm going to do is open up my sketchbook and import a couple of diagrams. Okay, in this first diagram, I'm depicting at the center the Earth with a little cross on top of it. That is supposed to represent the Earth in the case that it is at the center of the celestial sphere. The sphere that is on the outside, right here, is supposed to represent the celestial sphere on which the stars are located. Then this internal sphere is supposed to represent the sphere on which the sun is located. This right here is a location of the sun. Notice that the outer sphere is rotating about this axle that is given by AB. Also note that the inner sphere is connected to the outer sphere via an axle that runs in this direction from C toward D. So there are connection points down here at the bottom and up here at the top. So the drawing here represents the case where the Earth is at the center of the celestial sphere. So this is the position that Ptolemy is going to argue for. Notice the Earth is right on the axis, and it's also right at the center of the celestial sphere. You might say on the equator of the celestial sphere. Also notice I have another line drawn here, line HG. That line is tangent to the surface of the Earth. That line represents the horizon of the Earth if you were standing on the equator of the Earth. So the line HG represents the horizon for an observer that is standing on the equator of the Earth. So down in Quito, Ecuador, somewhere in northern Africa. This, by the way, is what Ptolemy refers to as sphera recta. Oops, I spelled that wrong. Sphera recta. That means a right angle sphere. That is, the sphere is at the horizon is straight up and down. It's at a right angle to the equator of the celestial sphere. Now, where am I going with this? What I'm going to argue is that if you place the Earth at the center of the celestial sphere, then all of the observations we see of the motion of the sun over the course of the year are consistent with what is predicted by this configuration. If, on the other hand, the Earth is not located at the center of the celestial sphere, then we're going to find that the predictions of the model do not match what is observed in nature. Okay, so let's just highlight a few points about what would be observed if the Earth, as is shown in this diagram, is at the center of this celestial sphere. Well, the first thing to notice is that if the sun is riding on this internal celestial sphere, then at the particular moment where the sun is down here, because this internal sphere has rotated around to the point where the sun is down here, from the perspective of somebody standing on the equator of the Earth, the sun will appear in front of a certain set of stars that are way down here on the celestial sphere. And as this outer sphere rotates around on a day-to-day basis, so remember this outer sphere is rotating around in this direction, the sun, from the perspective of someone standing on the Earth, will follow this trajectory given by this bottom dashed line over the course of the day. So it will move along this line and then back along this line as it's rotating around the sphere back to this point. So it will always stay in front of this star marked with a W over the course of the day. That, by the way, is the day of the winter solstice. Now, over the course of the year, what happens as this internal sphere rotates in the opposite direction, so in this direction right here, the sun is going to get higher and higher and higher, but on any particular day, as it rotates around, it's going to appear in front of some stars over here. When the sun is rotated a quarter of the way around riding on this internal sphere, it is going to follow a trajectory so that it's right in front of these stars, and that would be the day of the vernal equinox. Then, as this internal sphere continues to rotate, eventually the sun is going to be up here, and it's going to appear in front of stars that are way up here. So it rotates around over the course of the day, and it will appear in front of these high stars right here. That would be the day of the summer solstice. And then as this internal sphere continues to rotate around, eventually from the perspective of the viewer, the sun would migrate back down from being in front of these stars down through this point right here. That would be the autumnal equinox, and finally down to this point right here, where it would be in front of the stars of the winter solstice. So notice these two horizontal lines, the top one and the bottom one, represent the trajectory of the sun as it rotates around the Earth on a day on the winter solstice, the vernal equinox, the summer solstice, the autumnal equinox, and back to the winter solstice. So the sun always stays, from the perspective of the viewer, between these two bands. Notice now also that since this person is standing on the equator, the horizon line is straight up and down. That means that on any day of the year, the sun will spend an equal amount of time above the horizon, that is, in this region, and below the horizon in this region. And it doesn't matter if we're talking about the winter solstice, the vernal equinox, the summer solstice, the autumnal equinox, or anywhere in between those, the sun will spend half of its time above the horizon and half of its time below the horizon. So let's note that. For this observer standing at Sphera Recta, that is on the equator of the Earth, the sun spends about 12 hours each day above the horizon and 12 hours each day below the horizon. This is in fact the case. If you live in Quito, Ecuador, it doesn't matter what day of the year it is, you always have equal length days and nights. Okay? Now, what happens, how does this differ for someone that's not standing on the equator, but someone who is standing, let's say, in Milwaukee, Wisconsin? So what I'm going to do now is I'm going to import another image. Okay? Here's another image, and this image, again, the Earth is at the center of the celestial sphere. And this, once again, is what he is arguing for. But now notice that the horizon line, HG, is at this funny angle. The horizon line is tilted because the observer is standing in the northern latitudes. In the northern latitude. So, for example, in Milwaukee. Now, notice once again that as this large celestial sphere is rotating around on a day-to-day basis, if the sun is at a particular location, let's say right here, the sun will be following a trajectory around like this. And from the perspective of the viewer standing up here in Milwaukee, let me draw a person there just so it kind of illustrates what I'm talking about. From the perspective of someone standing up here in Milwaukee, they will look up at the sun, and the sun will be in front of these stars right down here. This would be the day of the winter solstice. As this large sphere rotates around, the sun will follow this trajectory through the sky. It will set below the horizon. It will be below the horizon for this entire amount of time. Then as this outer sphere rotates, it will come back like this. It will rise in the east and come back to right here. So it will spend this much time above the horizon and this much time below the horizon when it's on the winter solstice. Notice this makes sense because on the winter solstice, the sun is above the horizon for much less time than it is below the horizon. But now, as this internal sphere rotates around like this, slowly over the seasons, now the sun is going to be moving up higher and higher because after all, it's rotating around like this. Then what happens is on a particular day of the year, on March 21st, that would be the vernal equinox. Now the sun is going to follow this trajectory across the sky over the course of the day. And notice that on that particular day of the year, it spends an equal amount of time above the horizon and below the horizon. So let me emphasize this by drawing a horizontal yellow line. This is the trajectory of the sun through the sky on the day of the vernal equinox, March 21st or 22nd. Notice that this has an equal amount of distance that it travels above the horizon and below the horizon. So on the vernal equinox, the sun spends equal amounts of time above and below the horizon. In other words, there's an equal length day and night for someone standing in Milwaukee on this particular day of the year. Whereas on the winter solstice, on let's say December 21, that's the winter solstice, the day is much shorter than the night. That is, the sun is above the horizon for a much less amount of time. So notice that this line segment here is much less than this line segment over here. So that's daylight. And here's the daylight on the vernal equinox. And maybe I'll put a dark blue line here to represent this is nighttime over here. And this is nighttime over here. Notice also that as this internal sphere rotates more, so the sun is up at this part of it, it will appear in front of these constellations. And so this is the nighttime when it's on the summer solstice. And this line segment, the length of that, represents the amount of daylight during the summer solstice. So notice when this is, and by the way, I should say this, for this person, this is what he calls sphera obliqua. And because the sphere is tilted at an, or rather your horizon is tilted at an oblique angle, or an angle with respect to the sphere, whereas this one up here was sphera recta. So let me just draw this brown line here as a horizon line for someone standing on the equator, and this brown line here is a horizon line for somebody standing in Milwaukee. Okay, and again, to emphasize this, on every day of the year here, the sun is above the horizon for the same amount of time that it is below the horizon for someone standing on the equator. Like that, okay? All right. Now, what remains is the situation where someone is standing even farther north. So if someone were standing on the Arctic Circle, let's say, or even above the Arctic Circle, that's another case of sphera obliqua. And what I'll do is I'll do that sketch in the next lecture that I give. But where we're going with this is that all these kinds of observations that he's talking about with the Earth at the center of the celestial sphere are consistent with what we actually see in nature. Whereas if we take the Earth and we move it off of the center of the celestial sphere, then we would start having predictions that contradict what we see in nature. So I'm going to take a pause there, and we'll come back to this next time.